Good day to you. Thanks for joining our webinar today on the topic of is the power transformer failure keeping you up at night? So today's webinar will be in multiple parts. My name is Bhanu Srilla and I will be your first presenter. I will be presenting the first part of this webinar with information on the US power outage data, their causes and consequences, also maintenance methods and their pros and cons. And our second presenter for today is John Kolak. As many of you know, John is an award-winning author and a safety consultant, and he is the president of Praxis Corporation. John will present on various types of transformers, some of the common transformer failures and their causes. John will also cover overcurrent protections and arc flash hazards as they relate to transformers, and he will detail the importance of transformer turns ratio, also called TTR. Following that, I will provide a brief overview on Grace solution for continuous temperature monitoring, which is GraceSense hotspot monitor, and then we will follow that up with Q&A. As you go through this webinar, we strongly recommend you to type in your questions using the question pane on your webinar control panel, and they will be answered at the end. With that, let's go to the next slide. This slide shows the power outage information in the US for a 9-year period from 2008 to 2017. The information in this slide is retrieved from a blackout tracker report that was published by one of the major electrical equipment manufacturer, Eaton Corporation. As you look at the overall trend in the number of outages, it has increased from low 2000s to about 3,500 outages in the last 9-year period. So other point to highlight is the number of people who are affected by the power outage has more than doubled from just 2016 to 17 alone. And I'm assuming this is more so to do with the use of technology by the number of people. So another interesting point from the report is California, Texas, and New York states ranked the first 3 places for number of power outages. And the average duration of the outage is approximately 81 minutes. So why do power outages occur? We come across some of the inevitable causes like hurricanes, snowstorms, and wildfires. So others include aging infrastructure, operation and maintenance related issues like overloading conditions, short circuits, or selective coordination of the breakers. And last but not least, the human interaction with equipment, and in simple words, human error. Let's go to the next slide. So this chart shows the power outage cause by type for the year 2017. The key point I would like you to highlight in this slide is while the weather or trees was number 1 cause, which led to 1,159 outages, interestingly, the second top leading cause, which resulted in 791 outages, are caused by either faulty equipment or human error. It's pretty interesting that the equipment and the human error is the top second cause for all the outages. So let's go to the next slide. Let's take a look at the power outage and its impact on the economy. The image shown at the bottom of the slide was taken from the damaged power cables after a fire that caused the power outage at the world's busiest airport, Atlanta Airport, in December 2017. This power outage caused a shutdown the entire airport operations for about 12 hours. So reports from the utility company which was serving the airport and the airport sources confirmed the fire's intensity damaged 2 substations serving the airport, including the airport's redundant system, which is supposed to provide the backup power. The root cause of the fire is supposed to be a piece of switchgear that was in the underground electrical facility, failed, and it started the fire, which quickly spread through the tunnel and damaged the entire power system. This outage costed a major airline company that operates their hub in the Atlanta airport a staggering $50 million in just lost revenue alone. A study published by the ITIC states the average downtime cost across all industries is roughly $100,000 per hour. The study also states the overall downtime cost went up by about 25% since 2008. And again, the number is just an average across all industries. If you take the data centers, the data and monetary losses are significantly higher as they host multiple client data, specifically in the colocation data centers, in the data center space. So data center power outages report also suggests that the most expensive cost was found to be in the business disruption, which is followed by the lost revenue and also the end user productivity. So the numbers what you see here is about $740,000 for the average cost of a data center downtime. And if you look at the maximum downtime cost, that's almost $2,400,000. So power outage can have a significant impact, as stated, on the economy of the industry as well. Let's go to the next slide. Well, on the previous slides, we looked at the power outage data and their impact on the downtime, productivity, and bottom line. So let's take a look at what type of equipment failures really cause these outages. The information shown in this slide are for the years 2008 through 2013. These are the outages caused by substation equipment failures. And also, as you can see, the information sources are from multiple bodies. So one is NERC, which is a National Electrical Reliability Corporation, and TADS, which is a Transmission Data Availability Systems. And the last one is WECC, which is the Western Electricity Coordination Council. The key takeaway from this slide is circuit breakers rank number 1, which contribute to almost 39% cause for all the failures, and transformers ranks number 2, which contribute to 28% of all the failures. I'm sure the transformers and the circuit breakers are the core of your power distribution system itself. So let's go to the next slide. This slide shows the image from an arc flash incident that occurred at Facebook's Luleå data center in Sweden in 2014 and 2015. So Facebook and Schneider Electric talked about this incident at 7x24 data center conference in fall 2017. So what you're seeing here is a 5,000 amps overhead busway feeder of 10 feet sections, each weighing approximately 750 pounds, with about 2,000 feet linear installed at the facility. The facility identified the root cause of this failure as a thermal avalanche effect that resulted due to a loose connection at the busbar joint. So basically, inadequate tightening of the bolt resulted in this arc flash incident. This could have been a preventable incident if they had a right maintenance strategy in place with some kind of a forewarning and alarming. So we'll talk about the maintenance strategies in the next slides. Let's go to the next slide. Well, this slide shows the various maintenance strategies or maintenance methods that can be applied across all industries and also all types of equipment as well. So before you pick and choose the type of the maintenance for any specific equipment, you must have a better understanding of things like equipment criticality, downtime costs, and their overall impact on productivity. As you can see on the slide, run to failure maintenance, which is on your left, where do you do no maintenance? A great example is replacing a bulb when it's broke, right? So the next is the preventive maintenance, which is more of a time-based, which most industries do today. Like it's more like done on an annual basis or a semi-annual basis, or some facilities even do it once in 3 years on the type of the equipment based on the manufacturer recommendations or the facility defined routines. So a great example for the preventive maintenance is more like changing oil in a car for every 5,000 miles or 10,000 miles based on the manufacturer's recommendations. So the next on this list is the predictive maintenance, which includes basically sensors, imaging or remote monitoring and analytics. So basically in the last decade or so, predictive maintenance is getting more traction. That's primarily because of 3 main reasons. So one is the availability of the qualified personnel to perform the maintenance. Next is the availability of time. And the third point here is the high uptime demands and then the productivity pressures on the facility. And lastly, why mess with it when it's not broken? So more so predictive maintenance is getting more importance in last decade or so. So on the last one here, as you see, is the reliability centered maintenance, or we call it RCM, which is a kind of a hybrid model that takes all the 3 types of maintenance strategies and then optimizing them to a most cost-effective technique. So the primary objective of the RCM is to preserve the system function and to identify the failure modes which can affect the overall system function. And then the prioritize the system failure modes and also select applicable tasks or the maintenance functions to control the failure modes. So one key takeaway from this slide, as you see, is the cost of downtime goes significantly as you go from left to right, as you see it here. Also note that predictive maintenance also comes with upfront costs, like you need to make an investment for the sensors, the equipment, and the personal training, etc. So the best maintenance programs include all of the maintenance methods that are outlined on this chart based on the type and criticality of the equipment. So let's go to the next slide. So this chart shows the data from Department of Energy's Operation and Maintenance Guide. So as you can see, the top performing facilities utilize about 45 to 55% predictive maintenance programs compared to 25 to 35% preventive maintenance programs and only 10% reactive or run-to-fail maintenance. So while a top performing facility and an average facility, as shown in this graph, both spend about the same on preventive maintenance programs, which is 30 to 35%, the major difference is on how they compare on the predictive and run-to-failure metrics. So this chart below gives a great indication of current maintenance trends and their maturity models. The results further indicate that companies implementing the predictive maintenance programs have seen 35 to 45% reduction in downtime, 20 to 25% increase in the productivity, and also 70 to 75% fewer breakdowns, and about 25 to 35% reduction in maintenance costs as well. So this is a great tool to see where you want to have your maintenance programs from run to fail or the predictive side of it. Let's go to the next slide. So for your critical infrastructure equipment like transformer, switchgear, or any other critical component of your power distribution equipment, you may want to use a predictive or a reliability-centered maintenance strategy. Why? Because you can understand the equipment health, you can plan for a shutdown, and also you can coordinate the logistics and resources required to perform the maintenance. So most importantly, you can definitely avoid an unplanned shutdown which could significantly cost you. So this slide shows some of the key benefits of the predictive maintenance strategy and also a few things to consider while selecting the predictive maintenance programs. So with that, I will turn it over to John Kolak, who will talk on the transformer failures, troubleshooting, and transformer turns ratio. Thank you.
Thanks, Bhanu. As Bhanu said, I'm going to be covering three primary subject matter areas in my part of the presentation. The first will be common causes of transformer faults, both at the industrial level and the commercial level. Secondly, we'll be talking about transformer maintenance and testing. And thirdly, we'll be covering overcurrent protection on transformers with a particular focus on their impact on arc flash hazards in the workplace as well. Now, of course, a little bit of setup or preface would be important here. First is that the subject matter will vary considerably by a couple of things. Number one is the types of transformers involved. For example, the differences between oil-filled and dry transformers. And of course, the scale or size of the transformers also is important. So some of the discussion will focus only on transformers that would exist in a substation or in an industrial-grade utility operation, such as, for example, a paper mill or a steel mill. The rest of the presentation should apply to anyone who has a transformer. Now, I'm going to assume as I go through this presentation that the listener at least has a basic level of understanding of how transformers work, and we're going to be focusing primarily on three-phase transformer installations. Now, I want to be careful here that the sheer volume of information doesn't overwhelm you to the point where you kind of lose interest in the presentation. So what I'm going to try and do is strike a good balance there. I'll hit the high points, hopefully to make the key points of the presentation, and I'll leave it to you to use the question box on the software to ask any questions you have if you need amplification of any of the points we're making. So let's go ahead and jump into the presentation. Now I want to first, on this first slide, point you to the graphic on the right side of the slide, and it's called the so-called bathtub curve. What this is indicating is the failure rates of a system as a function of its life cycle from when it's first put into service to when it's retired after service. You'll notice that the curve is concave in this sense, and that there are two primary times when failure rates are highest. The first is what they call the infant mortality rate, which means when we first put something into service. And the other spike in the failure rates is at the end of the life cycle when the system is about ready to be retired. Now, this is an important consideration with transformers. the general rule with in an alternating current system, the general rule with anything that has a coil of wire in it is that it's a good idea to assume the potential for higher failure rates when you first energize the device. So for example, with a substation transformer, a large substation transformer, it would not be unusual when you first energize that device to let it soak. In other words, to energize it but don't load it with any current. We'll let it soak for a period of time, hours, even to days sometimes, to allow any internal faults that are going to develop to happen before we actually load the transformer and start putting it into service. So of course we want to take that into consideration on the front end when we first install transformers. Then the middle of the curve, the bottom of the curve, if you will, is the normal life wear and tear part of the system. The kind of things that affect how long the device will last include your work practices. For example, how many times you switch circuits into faulted circuit elements where the current is supplied by a transformer. That stresses the transformer. We'll talk about that. Also, engineering-wise, how hot do we let the transformer run? Again, when you overfuse the transformer, it doesn't mean the transformer will necessarily fail right away. It'll just shorten the life cycle of it. So even your engineering standards will impact that, and we'll discuss that more later on. And then finally, at the end of the cycle, when the system is already worn out and the transformer is ready to be replaced, of course, failure rates increase, and our system has to take into account what that means in terms of maintenance cycles and things like that. So now let's get into the meat and potatoes on this particular slide. The first thing to cover is the differences between mechanical and dielectric stressors in the workplace. Now, I think mechanical stressors are sometimes overlooked by folks when we think about electrical hazards. And what I mean by mechanical hazards are literally the electromagnetic forces that develop when a circuit is faulted, when there's a short circuit in the system, or even when you're picking up a large industrial load. When a lot of electrical current flows in a circuit, like during a faulted element, there are electromagnetic forces that develop that produce physical forces that are so strong that it can literally take metal bus bars and twist them like a pretzel in a sixth of a second or so. These magnetic forces stress the insulators in the system, and they stress the connection points in the system. So we want to make sure that we take into account the mechanical impacts on the system as well as the electrical impacts on the system as well. Under the dielectric stressors, by the dielectric we're talking about the insulation in the system. So this can include the actual bushings on the transformers themselves and also the winding insulation that are between the various turns ratio in the transformers, and the winding that's between the turns also has dielectric impacts. And of course, subjecting these devices, as I mentioned, to fault current can greatly impact the functionality of the system, whether it'll fail catastrophically, and its life cycle. Under the concept of overvoltage and lightning, well, of course, a lightning strike does produce an overvoltage event, no arguing that, but the impact on the insulation value of the transformer is important. So there's a concept that you'll see on your transformer nameplate called BIL, and that stands for basic insulation level. And typically a basic insulation level for a transformer, like in an industrial setting, would be 95,000 volts, regardless of the system voltage up to that value. And what they're saying here is how much over voltage has that transformer been designed to handle. So if you're in a part of the country that has a lot of lightning problems, you'll want to, of course, consider using a higher level of basic insulation level on the transformers that you spec out for your system. Overloading happens when there's simply too much load connected to the system. This can happen, as I mentioned before, either from just connecting too many loads to a transformer, or in some cases it can actually be done on purpose. For example, the fuses that you put in transformer banks, especially in a substation level setting, can greatly impact how long the system will last. For example, during the days when I was a lineman, we used to fuse our transformers at 150% of full load. That meant the transformer ran hotter than the nameplate value. A neighboring utility that we used to go and help out in an ice storm would fuse their transformers at 300% of full load. So the transformer was boiling hot on the pole by design, and what they were apparently doing is accepting the shorter life cycle of the device, using a smaller unit to feed a larger load, so to speak. So overloading can happen accidentally, or it can happen by design. Of course, inadequate maintenance is one of the leading causes of transformer failure, and we're going to talk about that under testing and maintenance, but that is certainly one of the causes of transformer failure. Within that subject, we talk about dissolved gases. When we get winding to winding faults in a transformer, now this is in an oil transformer under oil, the arcing that happens will produce gases within the transformer, among them acetylene. So by testing transformers periodically, we can monitor how much dissolved gas is in the transformer oil, and will give us an indication when the transformer is about to fail. And again, we'll cover that more later on. And the other type of contamination that can happen is moisture. This can happen because of a natural event like a flood, for example, or it can happen because of bushing, seals on the bushings leaking or things like that, where moisture or water can get into the transformer tank itself. And then finally, sabotage. I think we might be prone to think this is only a recent phenomenon with terrorism, but in fact, sabotage has been going on for decades. Early on, 30 years ago in my career, we had people trying to damage substation transformers by throwing logging chains across the phases of the transformer to precipitate faults. So this is not a new phenomenon, but it is certainly one we need to take into account, especially for transformers that will be difficult to replace. So let's go ahead and go to the next slide. Now, in terms of transformer troubleshooting, well, again, the difference between overloads and faults we've just discussed. Primarily, if we have an overload in the transformer, we want to figure out where that's coming from. Typically, we ask ourselves what's changed in the system. If the system was working fine, not overloaded, well, if it has a overload now, the smart troubleshooter would ask what's changed. The picture on the right indicates what happens when a transformer fault happens. And in particular, this is when our overcurrent protection did not function, obviously, because you can see that we melted all the conductors. Clearly, this is not how we engineered it, but that is an example of what happens when the transformer faults and maximum current or short circuit current flows and can precipitate those arcing faults is what happened in that picture. Part power can happen on transformers when there's internal fusing of the transformer and one or two of the three-phase fuses in the transformers blows. Usually when you lose one fuse, you might have the possibility for the bank, depending upon how it's configured, to try and continue to supply power to the system, and those would be what we'd call a part power problem. Again, it's an indication that you probably had some of the overcurrent protection actuate inside the transformer itself. Overvoltage or undervoltage, well, first of all, let's just talk about what we call the 10% rule. Now, the 10% rule applies to both current flow and voltage levels in a system. So the 10% rule with respect to voltage means that whatever the nameplate voltage is of that transformer, plus or minus 10% is within the realm of normal. So if you're on a 480 volt transformer and you read 512 volts with your voltmeter, don't start troubleshooting. That's within the realm of normal. And with respect to current flow, if you were to take ammeter readings on A, B, and C phase in the transformer, pick the middle number, not the middle phase, and plus or minus 10% of that is called balanced. So one of the things that can contribute to problems with transformers, if they're significantly imbalanced, meaning there's more current or amperes on one or two of the phases than the remaining phases. So that's 10% rule is kind of handy from a troubleshooting standpoint. With respect to tap changing transformers, well, one of the studies I've read suggested that 26% of the failures that happen in substations have to do with tap changers. Now, what tap changers actually do is they change the turns ratio of the transformer. We're going to be covering that a little later on, so we won't get too deep into that right now. But there are two types of tap changers in transformers. One are what's called load tap changers, which is what they're talking about here in the substation. These things they change with the transformer under load, and they do that to change the voltage output of the transformer to more accurately match what we need for our particular system. Every other type of tap changer in a fixed transformer is what we call a no-load tap changer, and more accurately, it should not be operated even when the transformer is energized. It's critically important to understand if you were to actuate a tap changer, a no-load tap changer, when it's energized, a catastrophic fault will likely develop inside the transformer. So overvoltage and undervoltage can happen for a variety of reasons. These are just a couple of those. The idea of a floating neutral means that the neutral is not grounded. It's not connected to planet Earth in some manner. The key point that I want you to get from this particular slide is that when the neutral is not connected to ground, and those three phases are not balanced, in other words, there's different current values on all three phases, or at least two of the three phases, you can have a voltage develop on the neutral of the unit itself. Now, again, I don't want to get too deep into the weeds here, but just understand that imbalances in transformers on certain types of transformer banks can produce a rise in voltage on the neutral of that transformer. and that can represent a shock hazard to the workers. Winding-to-winding faults we mentioned earlier, where the transformers are actually normally a laminated type core, and these windings are wrapped around them. There's insulation between the windings, and of course when that winding breaks down, it initially can produce the gases, internal gases that we mentioned, but as that begins to get more and more contaminated, it can actually begin to fault. And then finally, sudden pressure relays and substation transformers are critically important to understand. These relays sense when there's a change in pressure inside the transformer tank itself. And what it's telling you is that there's an internal fault probably in the transformer. Now, the sudden pressure relay is critically important to understand. It is really the only relay that we have in a substation. And I guess I should have mentioned these relays will only exist on substation-sized transformers. But if you have a sudden pressure relay actuated, it's going to lock out the transformer itself and probably the bus that it feeds as well. And it is the only device that we don't ever consider troubleshooting. You just simply tag out that transformer installation and call the manufacturer to come in and do their troubleshooting on it themselves. That's a good time to call in the cavalry, is when a sudden pressure relay trips the system off. So let's go to the next slide. Now, in terms of dry type transformers, what we mean by a dry type transformer is that the media that we use to cool the transformer itself is actually air rather than oil or gas or something else. And so the dry transformers are the most common thing you'll see in a commercial facility or a light industrial facility where we're converting, for example, 480 volts down to 120, 208 systems. So there's a few things to understand about dry transformers for this discussion. The first is that dry transformers run much hotter than oil-filled units. So for example, the nameplate on an oil-filled transformer might indicate that it is a 55 degrees centigrade transformer, which is like 130 degrees temperature, all the way up to, you can see the dry transformer in this example has its impedance value at 170 degrees centigrade. I think that's close to 400 degrees Fahrenheit. So one thing to keep in mind is that the actual transformer itself runs much hotter. So a dry transformer that's hot to the touch does not necessarily mean anything is wrong. Also, the type of transformer, the AA or FA or GA methods. AA means that it's a vented transformer. Its cooling media is just the ambient air in the area. There's no fans or anything on it. It just cools naturally through normal convective cooling. An FA transformer includes forced air, meaning that there are fans on the unit. And again, it's important to understand that transformers and even conductors, the ampacity, it's all about heat. It's all about heat. So you get a transformer that runs at 170 degrees centigrade, put fans on it so that it cools more efficiently, and you can get another 25% of load out of that same transformer. So in this case, forced air systems, usually in substations, will help allow a smaller transformer to feed larger loads. This is also true for outdoor transformers in the wintertime. They'll produce considerably more output in the dead of winter than they will in the dead of summer. And some transformers use gas cooling, less common, but that's something just for mention. Now, in terms of dry transformer maintenance, of course, infrared scans are critically important to note differences in temperature of the various components of the system. Measuring the high side windings to the low side windings, and then both of those windings to ground is recommended by some manufacturers. And again, let me preface or say this now, that anything I'm saying in this presentation, it is assumed that you will defer to the manufacturer's recommendations in terms of testing, loading, fusing, and things of that nature. But so the measuring is insulation testing. There's much more to know than that. And they also recommend that you visually inspect the windings when the transformer has been de-energized. Say, for example, if you have a plant shutdown, they want us to visually inspect those windings on an annual basis. And you're looking primarily there for arcing and especially dust and dirt accumulations. Let's go to the next slide. Now, in terms of transformer maintenance, well, some of this we've already covered, so we won't spend too much time on it. The first and probably one of the most common ones is the dissolved gas testing process. Here we will take an oil sample from the transformer itself and have it sent in for testing, and they'll give us a readout on a number of things, among them, like I said, the dissolved gases in oil. Resistance testing, and there are many types of tests to conduct. Measuring the high and low voltage windings we've already discussed. There are tests which we call power factor or dissipation factor tests on insulation, excitation current testing, meaning the current it takes to excite or start up the transformer. That can be very helpful to tell us if we're having winding-to-winding faults on them. So there are a number of different tests well outside the scope of this presentation, but suffice it to say there's quite a bit of testing we can do to predict whether the system will be able to function, and I think Bhanu will be talking about other ways to monitor, among other things, temperature in these units as well. Power factor tests on windings, bushings, and lightning arresters. In one particular study I read suggested a 3-year interval on that. Again, we'll defer to the manufacturer on that one. Keeping the insulators clean cannot be overstated, especially if you're in a dusty environment. One of my customers, for example, often will polish metal tanks, and there's a nice layer of metal flakes all over everything in the plant, it seems. And of course, aggressive maintenance would need to be there so we don't get conductive paths tracking, in other words, that would cause faults. Keeping the connections tight is also important. We mentioned earlier the magnetic forces that happen. So every time you turn on a large motor load, for example, excite a transformer, or have a short circuit fault in the system, all of those mechanical connections get stressed. So they need to be torqued down periodically, occasionally taken apart and wire brushed and cleaned up. So keeping the connections clean and tight is critically important. And for those of you that do have load tap changers, of course, you'd want to spend some time inspecting those and testing those to make sure they're functioning properly, so that they don't produce a fault when they change taps on a transformer. Let's go ahead and go to the next slide. Now, overcurrent protection and arc flash hazards is very important to understand, and I'll try and give you some insight there into how to read your arc flash studies as well, because this can be very helpful. First of all, it's important to understand that the overcurrent protection on a transformer is connected to the high voltage windings of that particular transformer. This will become important when we start talking about arcing time on faults. So that's one thing to consider. The difference between current limiting fuses and expulsion fuses is also important to understand with respect to transformer protection. Now, current limiting fuses are called that because they actually do that. When there's a fault in the system, it actually limits the amount of current that will flow in the system. And typically, the clearing time on a current limiting fuse is a quarter of a cycle. So it's a shutter speed on a camera clearing time. So current limiting fuses actuate best on high short circuit current events. The more fault current, the happier a current limiting fuse is. Contrast that with the picture that you see on the right. That's a typical expulsion type fuse in a transformer application. Now that fuse looks like a cigarette, and that is exactly the size of it. It is almost exactly the size of a regular cigarette. This fuse only has typically about a 1200 amp interrupting rating. So if you have a fault on the primary side or the high voltage side of the transformer, this particular fuse will not be able to react to that fault. And typically the current limiting fuse, if it has both associated with it on the transformer, normally the current limiting fuse will protect the transformer on the high voltage side, and the expulsion fuse will protect it on the low voltage side. And I'll give you some slides on that in the next couple of slides. So there's something called transformer turns ratio that you must understand here. We'll get through this subject and I'll hand you back over to Bhanu. Let's go to the next slide. Now let's take a look at the typical pad-mounted transformer application. So this would be more for utility grade or large industrial type customers, or the incoming transformer at even your commercial facilities. Now if you look at the little schematic diagram there, I've got a yellow line showing that the fuses there's 6 fuses, 2 per phase. Fuses F1, 2, and 3 are a certain type of fuse, and 4, 5, and 6 are a different type of fuse. So what you're seeing here is that the primary windings or high voltage windings in the transformer are where the fuses reside, and there's 2 different fuses associated with it. So if you look at it, let's go to the next slide. If you take a look at the legend for it down below, you'll see that fuses F4, 5, and 6 on the schematic are current limiting fuses. F1, 2, and 3 are protective links, meaning they're expulsion fuses. So what you can take from this discussion is that this transformer has complete transformer protection. The expulsion fuses would react to a secondary or low voltage side fault. The current limiting fuses would react to a high voltage side fault. So this transformer, if it were subjected to fault current, should be able to handle pretty much anything that happens inside of it. Although it's not hard and fast, that's a general rule. If you look at your transformer nameplates and there are no fuse indications or fuse symbols in them, that little squiggly line, then if there's only one set of those, you can assume it's going to be an expulsion fuse. And I would, just my opinion, I would recommend that you take additional care with respect to re-energizing that unit, because if there is a high voltage fault in that transformer, it likely will not be cleared by the overcurrent protection, and it will result in a larger arc flash event. Let's go to the next slide. Okay, let's talk about an important concept relative to arc flash hazards called transformer turns ratio. Now, the transformer turns ratio is found by taking the high voltage or primary voltage winding of the transformer and dividing it by the low voltage winding. This will give you a ratio in terms of both voltage and current flow between the high voltage and low voltage sides of a transformer. Now, what the TTR actually means in this discussion is that for every 1 amp you have on the primary winding or high voltage winding, there would be, in this case, 50 amps on the secondary winding. Important for you to understand that most of the work you're going to be doing will be on the low voltage winding, so you're going to be on the end that has the most current flow. Now, just from a troubleshooting standpoint, if you happen to know the full load amps on the high voltage winding, and in some transformers they actually give you that value, you can figure out what's on the low voltage side simply by multiplying it times the transformer turns ratio itself. If you already know the full load amps on the low voltage winding, you just divide it by the TTR and you'll get how many amps are flowing in the primary. So from a troubleshooting standpoint, that's kind of handy to know. Let's go to the next slide and let's put this to use. Now here you see a transformer winding, transformer nameplate I should say, that illustrates something from an older transformer. First of all, from our previous discussion, if you look at the fusing on this transformer on the nameplate there, you'll notice there's only one fuse in this transformer in each phase. And that would mean that this has only expulsion fuses protecting the transformer. And as we discussed earlier, that means it's worse for you if you were to have a high voltage winding fault in that same unit. It probably couldn't handle the fault. Now, if you look in the little box in the upper right, they're even nice enough to calculate full load amps for you on the high voltage winding. So at 34,500 volts, this 900 kVA transformer will draw 15.11 amperes. So they're nice enough to give that value to you. So let's go ahead and do a little short circuit calculation here and then illustrate what this means in terms of arc flash hazards. So looking at our list, we're going to calculate the TTR on this transformer. Number 2, we're going to note that the full load amps is already calculated at 15.11. We're going to use that ratio to calculate how much the full load amps is at the low voltage side of that same transformer. And then we're going to do a quick short circuit calculation on this. And we'll note that the transformer impedance right on the nameplate is 5.98%. So let's go ahead and put this to use, and you'll understand how it relates to the fusing and ultimately to the arc flash hazards with transformers. Let's go to the next slide. Now, if you look at the calculation on the left side at 690 volts, you'll see that the transformer turns ratio is 50 to 1, as we mentioned earlier. Full load amps at 690 would be taking the 15 amps right off the nameplate, multiplying it times the turns ratio, and that would mean on the low voltage or 690 volt side of this transformer at full load, it would produce 756 amps of current flow, and indeed that is correct. To figure out the short circuit current, we would just take the full load amps divided by the impedance of the transformer as a decimal, which is 0.0598. And that means on the low voltage or 690 volt side of that transformer, if you got a short circuit going, the system would produce 12,633 amperes of current flow. That's the side you'd be working on. Now, on the high voltage side, what do we've got over there? Well, we don't have to do as many calculations. We already know the full load amps is 15.11. So to figure out the short circuit current on the high voltage side, we would just take 15.11 divided by the impedance, and that means it would produce 253 amps of current flow on the high voltage side. Now take this right now, file this in your brain. This is important. If you get a fault going on the low voltage side of that transformer, you're going to see 12,633 amps at your location. The fuses on the high voltage side are only seeing 253 amps, which means they're not going to react as quickly as if there was more current flowing there. This is going to translate to an arc hazard for you. So let's go to the next slide and investigate this a little further. Now what you see in front of you here are what's called time current characteristic curves, also known as TCCs. And what it is, it's an inverse time ratio curve. So what it means is, as you see on the left side, if you have a high amount of current flow, the clearing time on the fault is relatively brief. Same curve on the right, if you have much lower short circuit current flow, the clearing time is much longer on that. And this is precisely the problem that's happening in an arc flash hazard. When you calculate incident energy, as the little line in the bottom of the slide says, it's directly related to the clearing time of the fault, not only the amount of short circuit current, but how long the fault lasts. Kind of like holding your finger in a candle. The longer you hold it in the candle, the worse the burns get. So from an arc flash hazard standpoint, what I want you to realize is those fuses are in the high voltage winding, which means the fault current is much lower than on the low voltage side. So the fusing isn't going to respond very quickly, and you're going to be working on the side of that transformer that has a lot of current flow, a lot of short circuit current, which means arc flash hazards for you. So here's my final point before I hand you off to Bhanu. When you're working on a transformer, from the low voltage windings, the actual termination points on the transformer, all the way to the first low voltage overcurrent device, like a circuit breaker, there is usually going to be a lot of incident energy there, tons of it typically, and there's really not much we can do about that. So keep it in mind that if you're working on the low voltage side of a transformer and you're between you and the transformer there are no overcurrent devices, there's going to be additional arc flash hazards and you'd want to take additional care. So with that, I'm going to hand it off to Bhanu now. I'll field your questions at the end of the presentation and answer them, and I sure appreciate your time. God bless.
Thanks, John, for such a great information on different types of transformers and their maintenance considerations. So what you see on the slide here is our GraySense hotspot monitor, so which is a predictive maintenance solution. So this device continuously monitors the temperature rise or hotspots that rise due to loose connections of bus bars, unbalanced loads, and also the temperature rise that develops due to harmonics as well. So some of the key things I would like to highlight with this device are basically this device continuously monitors the temperature, unlike thermography programs where you measure the data, like more so on an annual basis or a semi-annual basis. And thermography programs, what you see, the data is more so of intermittent readings, right? So with this device, you can continuously monitor and also log the temperature data. So the next point here is monitor the connections that are not visible to the line of sight. So with thermography cameras or the windows, you can only see what you can see with your plain line of sight. So the next one is a reduced risk, as you can remotely monitor and analyze the data as well. So there's no need to open the panel, and also you don't need to suit up with a heavy PPE, and also you don't require additional thermography training as well. So it can be also used on low voltage, medium voltage, and also high voltage systems. So this one, as it's tested for 80 kilovolts breakdown voltage, you may use this device up to 38 kilovolt systems. So let's go to the next slide. So here are some of the basic specifications for a hotspot monitor. The first and foremost thing is the device is CUL recognized, CE marked, and also FCC certified. The operational sensing range of the device goes from -4 degrees Fahrenheit all the way through 248 degrees Fahrenheit. And also we have an optional high temperature sensor which can take up to 320 degrees Fahrenheit. And the resolution is 1 degree Fahrenheit, and accuracy is plus or minus 3 degrees Fahrenheit. As such, there is no calibration required for the device. Everything is pre-calibrated at the factory level. All it requires is basically a 24 volts DC supply, and the device itself sits inside the low voltage compartment within your switchgear or control panel. Additionally, the device comes with a 16 megabytes built-in memory, which can store the data based on how frequent you are logging the data, and you can download the entire data using a .xl CSV file. And the last but not least, the device can be communicated using a Modbus RTU, Modbus TCP/IP, and also Ethernet IP protocols, which you can use to take the data to your DCS systems or a plant-wide SCADA system as well. Let's go to the next slide. So this slide shows the temperature sensing technology. We call it non-conductive contact sensing. So this basically works on a fiber optic technology, which uses an electrically non-conductive and thermally conductive technology. So in very simple terms, one end has a sensor tip and the other end is a polymer fiber, as you see it here on the slide, which is non-conductive. So basically, you can physically connect one end to a 38 kV system, which is a sensor end, using a ring style connector, and the other end connects to the module, which sits in the low voltage compartment, and what you see is basically a polymer fiber cable on the other end. So that's a non-conductive. So in simplistic terms, the device emits light and the light tunnels through the polymer fiber, and the change of light intensity at the sensor tip is measured back as temperature at the device. So you send the light signal through this polymer fiber, and at the phosphorus tip at the sensor, if there is a change in light intensity, that triggers back as the temperature reading, and that's how the device monitors the temperature. So pretty slick technology. Let's go to the next slide. So here is a quick graphic that shows how the sensor is connected to the surface or the connection that you want to monitor. So basically the sensor attaches to a connector of 6 gauge size using a standard 1/2 inch or an optional 1/4 inch ring style connector, and then the connector bolts on to the surface of the bus bar or the surface of you want to monitor the temperature of. So it makes it a pretty simple and secure connection. Let's go to the next slide. So this slide shows a couple of screenshots of the device web interface. So once you establish a connection to the device using the Ethernet port, you may configure the temperature set points, alarms, and thresholds using your computer or laptop. In addition, you can also change the network settings using unique IP addresses and gateway details using the network configuration tab. Lastly, as you can see the right side screen image, you can download the stored data on the device in a .csv file format to your computer for analysis and trending of the temperature data as well. Let's go to the next slide. So here are some of the screenshots for the hotspot monitor applications. As explained earlier, this device can be used in low, medium, and high voltage systems up to 38 kV. As the technology is electrically non-conductive, you may run the polymer fiber along the power compartment in your switchgear or secondary side of your transformers, and you can use this again both on low voltage and medium voltage MCCs and drives as well. If you're interested in a product demo, please complete a post-webinar survey and we will reach out to you after the webinar and set you up with one. So with that, John and I will stay online for next 5 to 10 minutes to answer your questions. And again, once again, thanks for joining us today.